Hi guys, let's go over this problem. Two loops of wire are moving in the vicinity of a very long straight wire carrying a steady current as shown in figure here. So I'll just show it here quick. And we have we need to find the direction of the current in loop C generated by there's a magnetic field flowing in this wire, so it's creating a magnetic field on both of the rings. So therefore, there's its own current because of Lenz or Faraday's law, which is Lenz's law. It's a bigger idea of Lenz's law, and then we also have these things are moving too. So let's go ahead and draw it. Let's just go here. Okay, that'll work. We have this current carrying wire, carrying current, and of course this direction. And we have a loop D, and we have a loop C. And loop C is moving up while D to the right. Let me just make sure that I have that right. Okay. And we're asked to describe specifically the induced current in these loops. So direction for both of them. So let's find that. First, what we need to do is we need to know, we know that for a current to be induced into these loops, we need a magnetic field emanating from somewhere, and that's going to evidently be from the wire. So use your right-hand rule, point your thumb in the direction of the current, and curl your fingers. You're going to see that we have a magnetic field moving in this direction where it's really strong here, and it gets more diffuse. I'll kind of try and draw this. The magnetic field gets diffuse as we move out. So that's what's happening. And notice that a flux here will be constant in loop C because, and if we use the right-hand rule, we have on this side of the page magnetic, and I'm going to draw these vectors to scale of their magnitude. So notice how we get more diffuse in the field strength as we move out, but the closer we are to the wire, the stronger it is. And what you're going to notice for this, okay, is that we're moving along a, you can kind of think this as an equipotential line, but for magnetic fields, because we're moving along this line where we're intersecting the same magnetic field strength. And if you remember that does not change the amount of flux moving through this ring. So there's actually, since there's no change in flux, we know that for there to be an EMF and thus a current, all right, so epsilon causes I, or the EMF causes I, we know that there needs to be, and proportional to, a change in flux over a change in time. Okay, well, time is changing, but notice the flux stays consistent, and flux final minus initial will cancel to be 0, and thus the EMF will be 0, and thus no current. So through C, there's going to be 0 current. But what about D? Well, notice for D, it's kind of the opposite case. If we use the right-hand rule, the magnetic field lines are going into the page, and I'll kind of elaborate the field strength here. So we'll kind of scale down, and then we'll get real small here, just to be thorough. Okay, so notice we're moving from a high magnetic field to a low magnetic field. So that's a decrease in flux. So delta flux, because the flux is decreasing, this is going to be a negative value. Okay, and if we think about what this means for Lenz's law, it means that because the flux is decreasing, And if I'm going to kind of tilt this on its side, okay, so imagine we just kind of tilt our frame of reference. It's still moving this way, but we're looking at the field lines. So we have a very big field line, and we're moving to a region of smaller field. Okay. So we know that the magnetic field points this way, but because the flux decreases, the change in flux vector, the way I like to look at it at least, I don't really know if it's a vector or not, but the change in flux vector points this way, which means the induced flux points in the same direction as the magnetic field. And because of this, we can use a right-hand rule and find that it's curling around this way. And if we bring that kind of back to our reality, so it's pointing with the magnetic field, that means it's going to go like this around the loop. So that would be a clockwise rotation, and let's see if they agree with us. And yep, that's going to be a clockwise rotation. And hopefully you can see kind of why this works out. I know it can be a little tricky, but the way I like to do it is look at where this like pseudo vector is looking at, right? Look where the change in flux is pointing. Does it point with the magnetic field or against it? Where is the magnetic or the induced magnetic field pointing? And that will lead you to find the right answer. But I hope you guys enjoyed. If you did, please drop a like, comment, and subscribe. I greatly appreciate it. Have a wonderful day. Bye-bye.